performance of flowing wells. So here we want to find out the main principle in flowing a well. What controls how much oil we end up producing? What is nodal analysis? What is the choke behavior? Yeah, have you done this before or not? Okay, I hope you haven't done it.
No, we haven't, sir.
Okay, so first of all, inflow performance relationship, vertical lift performance, single phase and two phase, and flow through the choke. And matching inflow and outflow, finding the final production rate and downhole pressure. So what we need to do, let's see, where is my, this is the well. And this is the reservoir. So we have two types of flow. One is flow in porous media. So when we are producing the oil from here, how much pressure drop we will have? This is called the drawdown. And relation between the drawdown and flow rate. Then now the oil or gas is here. How much energy we require to bring it to surface? So this is called inflow performance relationship. This one can be outflow performance relationship or vertical lift performance. And if you find these two pressure drop, then we can find out what is the flow rate of the well and what is the pressure at that time. What's the pressure of the well? Bottom hole pressure. And then from bottom hole, we can find surface pressure, and then we can go through choke and we can calculate the amount of oil that is being produced. And what is surface pressure, what is the after choke, how much we can produce. So basically, we can design both, find out the parameter that control flow in the reservoir and flow inside the tubing. The duty of production engineer is to effectively and efficiently dissipate reservoir energy. They want, because the energy is inside the reservoir. And when the energy inside the reservoir, we We can't waste it. Do you know how the energy in the reservoir is created or not? What causes that energy?
The depletion of the
energy is created because of water. Yeah, strange, huh? So imagine this is our reservoir. Here is water, oil-water contact, or water contact. And here is gas, oil, gas, contact. Okay? Imagine this is 10,000 feet from surface. Okay? 10,000 feet. This is 1,000. And this is 1,000, just for simplicity. So what is the pressure here? Can we calculate? So around 10,000 feet is depth of reservoir, and that is around 3,000 meters. What is the pressure here? Now, if you drill in canyon, after how many meters you reach water? Maybe 10 meters, huh? Some places 20 meters, some places 200 meters, okay? Desert, it might be 200 meters. But then compared to 10,000 or 3,000 meters, that's very little. So we can assume all the sediment are full of water. Okay? And here the pressure or pore pressure is P equal to rho G H. Rho is density of water. G acceleration, H is vertical depth. Are you happy with this? Density of water, if you can present density of water as PSI per foot. We use this because our depth matches with this sort of terminology. But you can say 1,000, kilogram per cubic meter, 1 gram per centimeter, you can calculate. But in general, for field cooperation, for field operation, we say that density of water is 0.45 per foot, psi per foot. Density of oil is 0.35 psi per foot. And density of gas, yeah, 0.01 psi per foot. So what is the pressure here? (4,500 psi). Okay? 10,000 multiplied by 0.45. So we are moving up. If you move up, is pressure reduce or increase? Pressure is reduced, but how much? What the column here, continuous column here is oil. Here is oil. So it would be 1,000 multiplied by density of oil, 450. So pressure here is all right. No, 350. 35 multiplied by 1,350. Okay. So pressure here would be 4,500 minus 350. So become 4,150. Do you agree? Because as we move up, the pressure reduces. So if you move to the gas, 1,000 feet of gas, the pressure is reduced. Yeah, 1,000 feet. So 1,000 feet multiply 0.1 become 100. So pressure here is 4,050. Okay, 100 below that. So we know the pressure inside the reservoir. Okay. What is the pressure outside the reservoir? What is depth? 8,000. Why 8,000? Because here was 10,000, 1,000, 1,000. Here it become 8,000. Okay. So far, so good.
Yes.
Multiply by 4, 5, because this is all water. Pressure outside the reservoir is 3,600. So pressure inside the reservoir is 4,050. Pressure outside the reservoir is 3,600. Now, if you do not protect, you will have a blowout, because pressure inside the reservoir is higher than pressure outside the reservoir. That's why we need to put a casing at top of a reservoir. That's why we have to have our casing 1338 at top of reservoir. 1338. Because otherwise, if you go with the same mud, you would have blowout. if you increase the mud weight to prevent the blowout, you might have fracture deformation above cap. That's why intermediate casing, we need to put it on top of reservoir. But you see that the energy of reservoir is from this water, the column of water, because fluid type has changed. Obviously, there are other activity. You can have tectonic activity to bring reservoir to surface, nearer to surface, or push it down further. But this is a normal reservoir. So that's source of energy. What is the duty of reservoir engineer or production engineer? Their duty is that to efficiently dissipate, use this energy for maximum production. That's the duty of a production engineer. So therefore, the production engineer should identify where I lose pressure, where I lose the energy. Yeah. We lose energy in the reservoir. We lose energy at bottom hole completion. We lose energy in tubing or casing, wellhead, floor line, choke. So anywhere, because if you don't identify where you lose energy, you don't know what to do with it. How to maintain the pressure, how to do not waste the energy. Why you shouldn't produce, you should prevent gas production. Because gas is like a spring, it's pushing the oil down. So you have to be very careful on how much gas you produce. So the pressure in the reservoir on the system, this is the production PI, productivity index. And you see that a lot of the pressure is depending on productivity index. If productivity index is low, you see that in reservoir we lose a lot of pressure. In tubing, quite a lot. As the productivity index increases, the loss in reservoir is reduced. But more overall percentage of pressure is lost in the tube. Yeah. So we need to identify where we are losing energy and think about how we can control or minimize the energy. Only across the choke, that's a different story. Across the choke, we might lose a lot of energy, but I explain why. Why we need the choke. Otherwise, you might say, oh, what you just connected together and we don't need any choke. Why we need to choke? So now, so inflow performance, vertical lift, and choke or beam for performance. So if you have flow in the porous media, that is the flow in the reservoir, then it has some rules and regulation, we use a modified version of the Darcy's law, because Darcy's law is designed for one fluid. And isotropic flow. But the principle is correct, and we use it as much as we can. So if you have something like this, a block like this, the flow rate, according to conservation of mass, whatever is going is, it should come out. But there is a pressure, and the flow will be from high pressure to low pressure. And the amount of flow is a function of pressure difference directly. The amount of flow is a function of the surface area. The higher surface area, the higher the flow. But inverse function of the length. The longer the length, less flow. And inverse function of viscosity. If you have high viscosity, you have less flow. So Darcy found this relationship, that flow rate is a function of pressure difference, area, cross-section area, the length of the section, and inverse function of the viscosity. The key point that Darcy found is that there is a number that can convert proportionality to equality. That is permeability. What is the permeability? Permeability is ability of a rock to have flow. Interesting point is that permeability is a function of rock itself, not fluid, of the rock itself, but not the fluid. So you use the same permeability if it is a gas, it is oil or water. It's a function of the rock itself. So this is the flow rate. This is the flow rate. If I divide the flow rate to area, become velocity. So velocity, flow rate divided by area, and then K divided by mu, because this is delta P. Delta P is P2 minus P1. So this is, there is a negative sign here. Negative sign here. So, definition of Darcy law and condition that Darcy law can be applied is mentioned here. And we cannot reach that condition. But it is a good foundation for using in application. The problem is that flow in the reservoir is not like this. linear flow. It's not linear flow. It is radial flow. Yeah, flow comes here, radial. Yeah, this is top view. So we need to change the Darcy's equation based on radial flow. If we have incompressible fluid, means that density and viscosity doesn't change because it's not compressible. So why viscosity should change? Furthermore, we assume it is single phase flow. Reservoir is circular with a radius of the reservoir. This is RA. This is well bore, radius of valve. And we can develop this equation for radial flow. Radial flow, we can have a steady state, unsteady state, and semi or semi-steady state. The steady state means that there is no change with time. Semi or semi-steady state is that the change in pressure with time is so little. That is valid for gas and gas condensate reservoir. Unsteady state is for oil that the pressure will drop unless there is a supply of fluid to the boundary of the reservoir. The steady states flow at the boundary of reservoir, and therefore everything remains constant. Steady state that dP to dr is fairly constant and does not change with time. So if you look at a well, top view of a well, this is the boundary of the reservoir. This is a depth, a diameter, and here is another diameter, and this one is closer. So what will happen that initially you start flow, the pressure signal, this is pressure, the pressure signal does not reach to the boundary of the reservoir. Pressure signal here. So the people here do not know if you have opened the well. And the maximum pressure drop will happen near to wellbore. Why? Near to wellbore, why? Because near wellbore, as we get closer to wellbore, the area for flow is reduced. You see that? The area for flow is here, is very big. So the same flow rate, if the area is big, the velocity is low. Velocity means that the pressure drop, frictional pressure drop would be low. If you get closer, the surface area is reduced. That means velocity is higher. And here is the maximum velocity near wellbore. So the pressure drop would be high. So this is a pressure profile at different time scale. So at time 1, at time 2, at time 3. Once the pressure signal reached the boundary, then is stable. And depending how this pressure drop changes, then we call it a steady state or semi-steady state if the change is very gradual and becomes sensitive. And this is valid, semi-steady state is valid for gas condensate and gas reservoir, because gas condensate is gas at reservoir condition. Yeah, and therefore gas is compressible and pressure drop will not change much. Initial condition, after a while it's reached to the dew point and then become two-phase. But natural gas is always gas in the reservoir. And if its pressure drop with time is very slow and dP to dr is constant, you see that here is constant, we call it semi-steady state. So we can write equation of flow based on radial flow. So we can write the area equal to surface area of this cylinder, which is 2PRH. Yeah, that's the area. R multiplied by 2 become radius. Yeah. Multiplied by pi become perimeter. Multiplied by height become area. So U velocity is a function of flow rate divided by at reservoir condition. This R means reservoir condition. And then we replace area with this number here. Okay. And that's equal to K divided by mu dP to dr. From here, we can write dP, pressure drop, is a function. This can be integrated between sand phase and radius of the well from here and radius of the drainage radius. So this is drainage radius, the outer one, and this is sand phase. This is RW, this is RW, this is RE, this is RE, this is RE. We can integrate it. Now, if we do integration for an incompressible fluid, so we are doing the integration, incompressible fluid, the flow rate doesn't change because it's incompressible. Viscosity doesn't change, so we can take it out of the integral. K doesn't change. Height of the reservoir doesn't change. So the thing that will change is change the diameter dr to r. And that would be natural logarithm of RE divided by R. PE, P boundary minus P reservoir, bottom hole, equal to drawdown. So we can write this equation. But we don't have anything to measure PE, because PE means pressure here. But we can measure average pressure. Close the valve, we get average pressure. But we don't have a well to measure at the boundary. So that's why we can simplify it. So here, we added, converted the Q to Q at surface. Q at surface is ore formation volume factor. Ore formation volume factor is volume of the oil at reservoir condition divided by surface condition, separator condition. So if you put these numbers, the equation would be this. You see that the flow rate, RE is constant, RW is constant, okay? BO is constant. Viscosity is constant because incompressible. So why viscosity should change? Therefore, you see that the flow rate is a function of delta P. So this is a straight line, something like this. This is flow rate. This is P well. If P well is equal to reservoir pressure, the flow rate is 0, okay? But as we drop the pressure, is a line that shows how much we produce. If you drop the pressure to here, this is the amount of oil that you produce from, that come out of the reservoir. If here, this is the amount of. This is called absolute open flow. When the reservoir is completely open, the pressure at the wellbore is 0. So this is the pressure drop. The slope is called PI. Yeah? And that is the relationship I mentioned, the straight line. This is a straight line. This is the pressure, reservoir pressure. This is bottom hole pressure and pressure. Semi-steady state means that the pressure will drop, but they are like parallel lines. dP to dr does not change. So dP to dr is 0 at reservoir boundary, and as R less than RE is constant. And this is C, isothermal coefficient of compressibility, which is change in volume to pressure divided by original pressure. And we do some work with the numbers. Finally, we get this number. A slightly compressible fluid, this number. You see that again, the flow rate is a function of pressure. So when the fluid is compressible or semi-compressible, we can determine the amount of oil production with pressure drop or drawdown, a straight line. But as I said, we don't have the pressure at the boundary. But what we can do, we can shut the well, and that will measure average pressure. We can get this number. So instead of pressure at the boundary, we use average pressure. So that this is P. And this, but the same correlation, but the number will change. If it is compressible, if it is like gas, when we do calculation, the same dP to dr, but now the pressure changes, the viscosity changes, flow rate changes. Yeah? So the equation become more complicated. And the resulting equation would be production. This is for single phase. For two phase, production is pressure to power 2. See that? Pressure to power 2 for production. So it is a parabola shape, something like this. But if you plot it based on P to power 2, then becomes a straight line. So for a gas flow, for a liquid flow, relationship is straight line. For gas flow, is this. But normally, we don't have only oil or only gas. Sometimes, most of the time, we produce a mixture. How about that? So this is for gas. You see that for power to power 2, pressure, average pressure to power 2, bottom hole pressure to power 2, and this is flow rate. So multiphase flow in the reservoir, some definition. In each pore, you can have gas, oil, and water. Water is always there. And this is saturation, means that such amount of oil per pore volume, amount of oil, water per pore volume, and amount of gas per pore volume. Now we have multiphase flow. When we have multiphase flow, we have to define relative permeability. So relative permeability is defined on the phase. So relative permeability to oil, it could be relative permeability to water, and relative permeability to gas. This is relative permeability. This figure, I don't know, have you come across this figure before?
No, sir.
No.
Yeah. This relative permeability is that permeability for each phase. And if you divide it to absolute permeability, then it would be 1 at each end, whether this is gas, whether this is oil or whatever. So here you have amount of this is for gas, this is for oil, Okay? So here is 100% gas. Permeability is 1. This is 100% oil. Permeability is 1, relative permeability. And then when you reduce the amount of gas, you see that is 100%, then it is 80%, then it is 50%, 70%. And then you see that as the concentration of each phase is reduced, then the production from that phase is reduced until you have a residual gas. This is called critical gas saturation. What does it mean? It means that you cannot produce this gas. And in other way, if the gas saturation is less than this number, we cannot produce the gas. That is the critical saturation. The gas composition should be bigger than this to become mobile. This is the difference between flow in a pipeline and flow in the reservoir. In pipeline, as long as you have new phase, it will produce. Nothing will be left in the pipeline. But reservoir is not like that. We need a critical saturation for a phase to move. And that's the reason we have connate water. Because connate, initially all the pores were filled with water. And when the oil or gas come invading that pore, they cannot remove all the oil and gas. Therefore, some water will remain. Some water will remain. So this is critical saturation of gas. This is 100% gas. And then when it is 100% oil, it will be something else. And this is the critical saturation of oil, residual oil. So we cannot produce all the oil. And how much is produced depend on their mobility. Gas is very mobile. So maybe critical saturation is 5%. Oil is less mobile. Therefore, residual oil can be 20%, 25%. That is the oil, no matter how much you try, will not be produced unless you use any of enhanced oil recovery technique. Okay? And obviously we can have water here as well. This is gas and oil. That would be 3-dimensional, but we can have it. So that control the flow in porous medium. If we have a mixture of oil and gas, then we use Vogel equation. This is German scientist. In English, we say Vogel, but in German, it is Vogel. You know, V in German is F, the sound of F. So here, we say that flow of the oil divided by maximum flow of the oil. And then you see that this is oil portion. This is gas portion. This is pressure drop because of the oil. This is pressure drop because of the gas. You see that to power 2. as we normally we are producing both oil and gas together, we need to make ourselves familiar with this equation. And this is some example. And this is Vogel equation and creating inflow performance curve. That inflow performance curve determine how much we can produce from reservoir. Sometimes the reservoir is above bubble point. If it is above bubble point, here a straight line, because it's above bubble point is single phase. Here, Vogel. And this is another example, another example, another example. And the effect of GOR. And I think that's enough for today.